In this video, I'm going to review a strategy for determining the electron configuration of an atom using what's called the reading left to right method. Just to recap from the last video, electrons in an atom are organized first into shells. There are 7 total shells corresponding to the 7 periods of the periodic table. The n=1 shell is closest to the nucleus, and the n=7 shell is farthest away. Electrons in the first shell are held very tightly, given their proximity to the nucleus, while electrons in outer shells are held more loosely. The outermost electrons in an atom are called the valence electrons, and those are the ones that are held most loosely. Electrons in the inner shells are termed core electrons, and those are held very tightly. Shells are subdivided into subshells. There are 4 types of subshells, the S, P, D, and F. S subshells can hold 2 electrons, P subshells can hold 6 electrons, D subshells can hold 10, and F subshells can hold 14. Electron configurations are an address system. They list the different subshells in an atom, and they also list how many electrons reside within those subshells. Subshells will fill in order of increasing energy, with lower energy subshells filling first and highest energy subshells filling last. And the electron configuration ends with the terminal subshell. And the terminal subshell is the highest energy subshell in a given atom. Highest energy occupied subshell in an atom. To determine the electron configuration, first we have to label the periodic table. And the first step is always to label the periodic table. I'm going to go ahead and do that. So over here, I already did this, but here, helium is usually located above neon on the periodic table. I erased it here, and I'm going to place it next to hydrogen because that comes in handy when determining electron configurations. I'm going to first label the 7 periods. Over here on the left, I'm just going to label this 1, 2, 3, 3, 4, 5, 6, and 7. And if you'd like, you can also add an S over here. Just to indicate that here, everything in these 2 columns corresponds to terminal subshells that have the S designation. Over on the right side, starting with boron, I label 2p, not 3p, 2p, 3p, 4p, 5p, 6p, 7p. Starting with scandium, switch colors. Over here, I'm going to label this 3d, 4d, 5d, and 6d. And then down here, starting with cerium and thorium, I'm going to label this 4f and 5f. Let me change the colors over here too, just so they're a little bit easier to see. There we go. Why did I start with lanthanum and actinum? Or sorry, why didn't I start with lanthanum and actinum? Actually, lanthanum and actinum. So if I take lanthanum, lanthanum is actually right here, and actinum is actually right here. They have a terminal subshell that is of the D type. And so they are often included here in this inner transition block. But for the sake of electron configurations, just remember that the f orbitals start with cerium and thorium. The reasons for that are very specific, and they're much more advanced than what is covered in the scope of this class, so I'm not going to go over them. Just remember that cerium is the start of the F subshell, the 4F subshell. Okay, I'm not done labeling yet. So I have to label at the very top now, above hydrogen. All elements in this column have a terminal subshell configuration of S1, and all elements in this column have a terminal subshell configuration of S2. Starting over here with scandium, recall that the D subshells can hold 10 electrons. So for scandium, yttrium, lanthanum, and actinium, these have terminal subshell configurations of 3D1, 4D1, 5D1, and 6D1 respectively. And I just do D1, and then here I'll do 2, 3, 4, 5, 6, 7, 8, 9, and then D10 over here. Above boron, elements in this column have a P1 terminal subshell configuration, and then P2 for carbon, P3 for nitrogen's group, P4 for oxygen's group, P5 for the halogens, and P6 for the noble gases. And then finally, for the F subshell, starting with cerium, cerium has an F1 terminal subshell configuration. Praseodymium has an F2, then F3, F4, F5, F6, F7, F8, F9, 10, 11, 12, 13, and 14. Let's do the electron configuration for, get this over on the side. Let's do electron configuration for rhenium, Re75. Rhenium has an atomic number of 75, which means that a neutral rhenium atom also has 75 electrons. So the second step in determining the electron configuration is to locate the element and determine the terminal subshell configuration. And so rhenium, Re, is here. It's number 75. It is in the 5D block over here. Notice it's 5D. And it has a terminal subshell configuration of 5D5. We know that because it's in the same row and column, so it has a 5D subshell. Its highest energy electrons are in the 5D subshell. And here, it's in the fifth column in the C block. And so it has a terminal subshell configuration of 5D5. I'll write that down here. So it's 5D5. And then the last step is just to read. How do you read off the electron configurations? So I'm going to read the electron configurations off by reading the periodic table left to right. And then I'm going to write down my electron configuration down here as I read. And so, and choose a nice color. I start with the first period. And as I complete each period, I'm just going to increment down a period. So for the first two electrons, they go in the 1s, they go in the 1s orbital. So it's 1s2. And now I increment down to the second period because my first period is done. It goes 2s2, 2p6. And then I'm done with my second period. So now it's 3s2, and then 3p6. Now I'm in my fourth period. Goes 4s2, 3d10. So notice how my 4s goes into my 3d. And then it goes 4p6. So it goes 4s2, 3d10, 4p6, and then 5s2, 4d10, 5p6. So that's 5s2, 4d10, 5p6. And now I go 6s2. And after the 6s2, notice I enter this lanthanide series. And so sometimes it's useful just to draw an arrow down here, just to remind yourself that when you're going to the lanthanide series, you're not going to continue on into this 5D subshell, but instead you're going to go down here, and it's going to go 4F14, and then back up, and then finish off the would-be 5D10 if I went all the way to Hg mercury. But notice that rhenium is over here, number 75. So I'm going to end here with 5D5. And that is the electron configuration for rhenium. This is the full electron configuration. What about the abbreviated electron configuration? If I want the abbreviated electron configuration, all I need to do is count backwards from my 5D, 4F, 6S, and find the last filled p orbital, p subshell, sorry, and it's 5p6. If I go up from rhenium, up here, one row, and I go all the way to the right, everything from 1s2 all the way to 5p6 corresponds to the electron configuration for this noble gas, and that's xenon. And so I can go ahead and I can abbreviate this whole thing XE, and then just adding on everything that comes after this 5p6, after this xenon electron configuration, would be XE, 6s2, 4f14, 5d5. So here I've determined the full and abbreviated electron configurations for rhenium.